Please welcome Brian Schmidt, Australian National University.
Hello, I'm Professor Brian Schmidt, Vice Chancellor and President of the Australian National University. I would like to start by acknowledging and celebrating the first Australians on whose traditional lands I'm joining you from, and pay my respects to elders past and present. Here at ANU, we pride ourselves on our people and the research and innovation excellence that delivers solutions to making our world a better place. Scientific rigor and a brilliant idea have combined with a strong team and commercial acumen to build quantum brilliance. This is something we strive for, to advance humanity. And that's why we have nominated Quantum Brilliance to Falling Walls Enterprise. The foundations of quantum brilliances stem from a decade-long scientific collaboration between our university and the University of Stuttgart. It is great to see the success that Andrew and Marcus have made of quantum brilliance in Australia and its subsequent expansion into Germany, where we can share scientific advances, R&D expertise, and manufacturing know-how in a venture that we will hope will become as much a success in Germany as it is here in Australia. To me, this represents the true spirit of this conference, and it is why I believe Quantum Brilliance has an excellent chance at winning Falling Walls Venture 2021. Good luck, and hope to be able to join you in the future.
Breaking the wall to inaccessible quantum computing. Mark Mattingly Scott, Quantum Brilliance.
There is a race going on. Some of you already heard about quantum computing. It's a thing at the moment. And the race is about how do we exploit, how do we leverage, how do we use quantum computing. It's a global race, very much a global race, a geopolitical race. And it basically talks about a technology, the physical principles of which were laid down over 100 years ago. A lot of them by scientists, physicists from Germany. The physical principles, although they're well understood, the exploitation of those physical principles, the exploitation of quantum mechanics, has taken a long time, and it's only recently that we've learned how to do that. But the technology will be transformative. It represents a potential for incredible value, and is almost certainly going to change in a similar way that the Silicon Revolution, the semiconductor revolution did, the way we do almost everything. But the challenge, of course, the elephant in the room is, what's the first step? Here on the right, you'll see a typical quantum computer. This illustrates one of the tusks of the elephant in the room, which is that quantum computers are associated with infrastructure costs. They are basically physics experiments, complicated machines, which you need to cool or apply high precision lasers to. Quantum Brilliance is, we are going to miniaturize the way you do quantum computing so that ultimately it'll be something you can fit inside a lunchbox. It'll be a CPU, GPU kind of device. The thing about using diamonds, however, for quantum computers, you need to create an environment where you have a quantum system. You need to be able to interact with that quantum system, and you need to keep it in isolation. And isolation is the hard part. The control is rather simple, and nature gives us in diamond a material where you get the isolation more or less for free. We don't have to fight nature to get a quantum state. It comes for free. What this means is we can leverage and use the playing field. And this will allow us to get into a situation where we're able to put diamond quantum computers almost everywhere. So both in terms of massively parallelized quantum computers, so instead of a quantum supercomputer, you will see lots of small quantum accelerators in a compute center, but we're also going to be seeing this technology being used at the edge in robotics, in process control, manufacturing. The company is started in Australia. We're expanding into Germany. We're going to be getting up to 150 people by the end of the year. I'm the managing director here in Germany. The founders are all from Canberra. One of the advantages of the technology is it's not tied to the cloud. So in terms of actually using it, exploiting it, we can think about applications in aerospace, in robotics. Basically, wherever you have the data, this is where you're going to be able to put a quantum computer based on diamonds. The market potential is probably going to be around, the estimates say around $50 billion by 2035. But if you look at the value at risk, which is the disruptive potential of quantum computing, it's in the trillions. The success of the company is basically going to be that we will outperform computing on an ongoing basis by having a material which scales, which is miniaturizable, where performance improvements are incremental. We generate a vacuum of investment. So very similarly to the semiconductor industry, the potential for creating a scalable and continuous investment in quantum computing is there. There's minimal capital risk, negligible operational expenses, and we're the only company who are able to do that. And Diamond Quantum Computing will normalize quantum computing. Thank you.
Thank you. Oh my God, okay. So first the jury, but then you, and then you. It's easier logistically.
Yeah. Thank you very much. I think you left out quite a lot of information, so I guess you will have plenty of questions. If I understood correctly, yours is one of the methods of quantum computing, and the ones that you hear about most are, of course, ion traps and superconducting. And we always hear that yours is behind. So the first question would be, how far is it behind? You were saying you have hardware available, so it would be good to know where we stand, how many qubits we have, and you know, when we can get our hands on it. So if you could tell us a little bit more about that part, would be really appreciated.
So the first machine was sold to Pawsey Supercomputer Centre in Australia. We're in the process of acquiring, engaging with further customers, especially here in Germany. I can't tell you who, but if you're interested in buying one, just reach out to me this evening.
Tell us specifics about the machine. What sort of machine is it, what you're currently selling?
It's it's basically a 19-inch rack unit, 6U unit. So essentially you have a power supply connector and an Ethernet connector on the back of it. Obviously you have APIs and ways to interact with that machine. But there's no cryogenics, there's no special lasers, there's no hard stuff to do. It's just a power socket and an Ethernet socket. One 19-inch unit. Number of qubits? Well, the machine at the moment is a handful of qubits. We know how to get to 50+ qubits. The next question that's probably coming up is, well, what about the Honeywells and Googles and IBMs of this world who are promising thousands of qubits? That's maybe a valid question, but those companies are comparing themselves because they have to compete with high infrastructure systems, always to a supercomputer system. Our market, our target, in order to achieve incremental rollout, incremental development, is to say, as soon as you've got a quantum computer which outperforms a comparable graphics processing unit or central processing unit, and we call this the idea of quantum utility. As soon as you've got that, then the business case and the ROI is there. You will be able to justify the expenditure, and it will also make sense because you will outperform those particular units for very specific use cases. That's a long answer to your short question. I'm sorry. I hope it helps.
Okay, we have a very tight time. I would like to give the priority to the jury, if that's okay for you, please.
Yeah, thank you. So you talked about approximately a handful of qubits, or 5. The second question then is about the quality of your qubits. Can you tell about that?
Yeah, so the classic measures of quality are things like coherence time and error rates. Diamond at room temperature has a coherence time of several milliseconds. The error rates we currently have with the first machine are in the third digit, so 99, 99.9. We expect to be able to improve that. The number of qubits we are aiming for, like I said, where we know we can get to is we estimate we will get to this point of quantum utility within the next 3 years.
Okay, sorry, I skipped your question. You were the first, actually, so please. Yes. We have 30 seconds left.
When you're parallelizing the quantum chips, can you sort of maintain the quantum properties across this parallelization, or is this lost?
That's a very good question and a very long answer.
No. We have 4 seconds left, so yes or no?
Maybe.
Okay, so I would say, I'm sorry for this, I have to interrupt this, but you know we have the get-together afterwards, so you will have the opportunity to get in touch with everyone. Thank you very much.
Thank you. Thanks.